AP Chemistry students. Le Chatelier's principle is actually a very elegant, beautiful way that systems in equilibrium relieve their stress. Le Chatelier's principle tells us that when a system in equilibrium does experience a stress, the system will shift in a direction that relieves the stress, and eventually a new equilibrium will be attained. So what are possible stresses? Well, if we have a system in equilibrium, we know it's worked to get there. So what could cause that to go astray? Well, if we change amount of reactant, if we add more reactant or remove some, or product, if we add some or remove some. Now, of course, though, if we have an equilibrium where one of our species is a solid, then we know that does not affect the equilibrium position because it doesn't impact the equilibrium value. Strange, isn't it? Only species that are gaseous or aqueous, of course. Okay, if we would adjust temperature, if we would do something to change the volume of the vessel, well, that's going to, of course, cause a change in pressure. These usually, of course, go hand in hand. So really, there's just three main stresses. Now, what is not a stress? Well, again, if we change the amount of something that is not actually part of the equilibrium expression, that's not a stress. If we would add an inert gas, for example, helium, non-reactive gas, well, that's going to change pressure, but it doesn't take part in the equilibrium expression. And so no, it's not going to be a stress on this reaction. If we add a catalyst, that just helps us to get to equilibrium faster. So no, that's not going to be a stress. And if we change volume or pressure on a liquid or a solid, we know that these only are seen as stresses on the gaseous state. So we just have to be cautious because not every manipulation could be seen as a stress on that reaction. So let's look at some specific examples. Let's take a look at this reaction. The Haber-Bourne process to make ammonia. So our equilibrium expression is, of course, NH3 squared over N2 to the first, H2 to the third. Everything a gas. Well, what if we change amounts? So we know that this reaction has worked its way to equilibrium. It has concentrations of everything that deliver the same K value that we know is dependent upon temperature. Well, what if we would change the amount of something? So let's go ahead and add some more nitrogen, add more reactant, and that, of course, is a gas. It does show up in the K expression, so that is going to stress out the balance. If we would add nitrogen, that throws us out of equilibria. So what we could do is find a new kind of where are we value and calculate Q, because we're no longer at equilibria. So what we're doing is we're increasing the amount of nitrogen. We're increasing the denominator, so Q, because we have a larger denominator compared to what we would have at equilibrium, is going to be less than K. So what's going to happen? The reaction will shift to the right. You know that. We are going to make more product. So to reach equilibria, we could say many different things. The reaction shifts right. The reaction favors product, or it favors, movement in the forward direction. We could say that the rate of the forward reaction will exceed the rate of the reverse reaction. Because what the reaction is trying to do is get back to the same ratio because we haven't changed temperature. So we need to diminish some reactant, produce more product to try to get ourselves to the same K value. If we want to look at it graphically, So if we began in equilibria, we know the concentration of our different species was constant. And what did we say we did? We increased nitrogen. So if we want to, use that, my red line here, and say, oh, we increased nitrogen. Well, the reaction wants to decrease some of this. So it's going to work to get this to be less. Okay, well, how do we do that? We're going to make more of this. Okay, but in order to react this way, we're also going to decrease some of that. So this decreases. And then we end up, getting ourselves back to equilibria. So we're not going to be exactly the way we started, but these should give us the same ratio and the same K. If you add reactant, the system will shift to form product if those things take part in the equilibrium position. If you add product, it's going to shift to reactant, again, to try to regain that same ratio. That's if you add. So if you add, it's going to move in the direction to remove what you've added. Well, what if you take away? So what if we would remove nitrogen? Well, then the reaction is going to try to replenish what you removed. So the reaction to try to, reestablish equilibrium, the reaction will shift left, will favor reactant. Again, these are all different ways of saying the same exact thing. Or the rate of the reverse reaction, and so we're going to be out of equilibrium, will exceed the rate of the forward reaction. And then, because we haven't changed temperature, we haven't changed the reaction, once we get the ratios okay, we're back at equilibrium, and then the amounts will stay constant. So if you add, it will shift in the direction to remove it, but if you remove, you shift in the direction to replenish it. All right. What if we change volume? Well, remember, a change in volume will result in a change in pressure of gases. So, if we would change volume so we increase pressure, and that, of course, would be a decrease in volume. That's going to increase pressure. Well, that's going to stress out the gases. So, it is going to then favor the side with less number of moles of gas. So if we decrease volume, okay, then the side with more moles of gas is going to experience a greater stress, and the reaction is going to shift to take some of that away and make make more of the side that has less moles of gas. But if we want to think about like the chemistry that's going on, if we decrease, then we're causing the molecules to collide more often. And we're going to get a greater amount of collisions. We need, 2 of these for every one of these. So we're going to be favoring reactant. If we would increase volume, well, that's going to decrease pressure. So it's going to seem, oh my gosh, like we're losing gas. Well, then what direction can help us replenish gas more? We're then going to shift right. And so if you minimize pressure, well, then you're going to shift to favor the side with more moles of gas. And again, it's all in the hopes of retaining the same K value. But if we also want to talk about gases, if there's no change in temperature, there can't be a change in pressure. So how do we, increase the number of collisions to deliver the same pressure that was prior to the stress? All right, next. Well, what if we change temperature? Well, what we need to know is our reaction exothermic or endothermic? So we know if the enthalpy of the reaction is positive, then we know it is endothermic. That heat is required for the forward direction. It is endothermic in this direction. So what if we increase temperature? If we increase temperature, we're adding heat. We are encouraging the endothermic direction. Some teachers really like to say, well, if it's endothermic, we can apply heat as being a reactant. So if we increase temperature, it's like we're adding reactant. Better terminology is that it's going to favor the endothermic direction. That's just a more eloquent way of saying that. And then we're going to shift to the right. Now, if we change temperature, we get a new K value. So if we're changing temperature and we're favoring the endothermic, we're going to be permanently making more product than reactant. So then our new K value will be greater than previous to the increase in temperature. It would be, of course, the opposite. If we decreased temperature, then it's going to favor the exothermic direction. Okay, it's as if we're removing heat, so we're going to shift in a direction to replenish that. And if we're moving toward more reactant, then we know that our K value, if we change temperature, will change, and it's going to be less than what it previously was if we're shifting left. All right, if we take a look back at the Haber-Bourne process, so I just want to, this reaction is exothermic, and we know that because we're given the enthalpy, and we know if enthalpies are negative, we are releasing heat. So if we decrease temperature, then we are going to be, we could look at it, okay, heat is a reactant or a product, and we're removing product, but we could also say that if we're decreasing temperature, okay, we are going to be shifting right, trying to replenish that. If we decrease temperature, we are going to be favoring the exothermic direction of the reaction, which is right. If we would increase temperature, well then we're going to be favoring the endothermic. We're adding, and so it would be reactant shifted in the case of an exothermic if we are increasing temperature. So interesting that, we know that an increase in temperature increases the speed of our reaction, but it doesn't necessarily, depending upon the exothermicity of our equilibrium, cause more product to necessarily form. In this case, it's going to cause less. So interesting for us. Now, let's imagine you're a chemical engineer, and your boss comes to you and says, okay, here's our reaction. We need to increase our yield. So you have some options. What will give you kind of the biggest bang for your buck? Well, that's going to take some experimentation, because it depends on the cost of your reactants and also the temperature at which you need to run it. So back to this Haber-Bourne process, well, it's exothermic. Okay, if we want to increase the yield, we want more product. So what stress can we do to get our reaction to favor more product? Well, if we increase the concentration of our reactants. And they're both gases, so they both influence the equilibrium position. Okay, that's going to help, get more product. All right. What about volume? Do we want to increase or decrease? Well, we want more product. And there's 2 moles of gaseous product, and there's a total of 4 moles of reactant gas. Okay, so if we decrease volume, that's going to stress the reactant side. And we're going to push to make less moles overall of gas. So if we decrease volume, that should cause, more NH3. And what about temperature? Okay, well, it's exothermic. Exothermic. So if we decrease temperature, it is going to favor the exothermic direction, and we'll get more ammonia. So we can use Le Chatelier's principle to our advantage. I would venture to say, ladies and gentlemen, that Le Chatelier's principle is going to come in some way, shape, or form to us on the AP Chem exam. So we want to be prepared to be able to interpret, okay, what exactly will the stress do on the equilibrium? What direction will it shift? Will that cause a change in our K value? And we can't forget that we could implement a stress to increase or decrease the yield of a reaction.